All right, so here we are picking back up on the program we were working on. So we have a couple things we're making use of from the math library. Uh, Also, we're defining pi. We're going to get farther into libraries and definitions, but we're going to borrow some from Dr. K's content because he's got a much more succinct explanation of libraries and how they work than what I've been able to come up with. So he conveys the information in about half the time, roughly. He's very efficient and gifted in that particular way. So, um, yeah, there's a lot of things that we're trying to do with this. We start with including this library. We're going to still need to add our variables for multiple calculations. We are starting with a couple functions that we defined. So this is a function with a floating point, meaning decimal output, called triangle height calc, that takes advantage of two variables that are also stored as decimals. So floats A and B. Then we have a couple internal variables, so local variables, HT and temp. Temp having to do with being half the base to use in the calculation. Square root and power are the functions that we're making use of from the library in order to calculate the height. So fairly straightforward function. In our setup, we're going to need to do a couple more things. We need to do the Pythagorean, and we need to do the triangle area because we don't have those yet. Our loop is going to be, for this one, intentionally left empty. Because we only want to do one run through of the calculation, so we can run it in setup. That'll execute one time. Coming back up here, we have our serial port that gets open and it waits while the serial port is still opening. Then we define some variables that we're going to use. So we're defining the variables in a string here, not to be confused with defining string variables. This is just a variable string that's going to be all of the float type, the integer type, and some more of the float type. These being local to setup, they can be used by anything that's inside of setup. We're also likely going to end up defining some variables outside of the setup and outside of the other functions so that they can be used in any of these functions. So we'll take a look at that in a little while. So we define our variables. Then we start asking for user input. What kind of triangle is it? Then we're looking to parse integer. So if they type text, it won't bring through gibberish. So we're looking specifically to do a serial parse integer. While serial available is comparable to 0, means that while there's nothing there, just wait, then internalize whatever integer is there, store it to this try-type variable. Then we need the length of one side. Then we need the length of the second side. Then we need the length of the third side. And this will give us the information that we need in order to do a couple more of the calculation steps. But we do have to go ahead and define what our Pythagorean is going to be. So we need to add a couple more functions here. There we go. A couple more still jumping in. So we're going to need another instance of a float So the variables this is going to need to take in, again, you kind of get to cheat in this case. You're not really creating them completely from scratch. You're creating them for a specific purpose. Height and temp. So here, for the Pythagorean, is you need your arguments, and you need to define them as variables in this case. So we've got float A and float B. You know the formula for the Pythagorean theorem. This is simply going to be create our variable that we need. So you create this variable for the calculation internally. We're going to do a square root of 2 powers close that. So the first one is going to be A2. Second one is going to be B2. So this takes the squares and gets the sum. There we go. So this takes the square root of the sum of the squares of A and B. So A squared plus B squared equals C squared. The square root of those gives us the value for C. So this undoes the operation of the theorem to return C. And then we can type in something that we haven't really used much yet. So this becomes of critical importance. If we don't use return in this circumstance, we can calculate something inside a function and it never does anything with the value. Even if we assign it to C inside the function, nothing outside the function is able to access C unless we tell it to return the value for C. We don't often do this in a lot of these. And there's kind of a couple reasons why. So this one, for instance, this is one of the points where for this triangle height calc, we need the same thing. We need to use a return. I'm glad we had to stop on that point because otherwise we were going to have to diagnose why the thing was calculating. I don't want you guys to have to quite troubleshoot at that level yet. Later, yes. Now, no. This will at least give us a fighting chance of getting these things all pulled together. So we're going to return HT. We're going to return C. We're going to need our next function, which is going to be yet another float. And there's a couple ways that we can go about this. But we're going to calculate the area. So we're calling for try area. So we're going to do the same sort of thing. So will also be a float. And area has to be exactly the same capitalization, title case or not title case, etc. So this has a variable we declare inside called, and it can be spelled just so long as it's consistent. You could spell this area whatever and it wouldn't care, just so long as you know what the variable is. This is a local variable, so it's only internal, but good naming practices should still apply. So this is 0.5 times the base times the height. So we know that from geometry. This one is super duper complicated. This next step. Return area. So we need our arguments. So this is how we define the triangle area. Same sort of idea. So it puts the area for use outside of the function. So we need this to be able to get a value back out of what we're doing. It could be HT. Inside the function, it can be for the sake of consistency in the code. In this case, we aren't using we aren't necessarily using the HT from up above, because the function, this is the entire world of the function. This defines the world of the function in full. So the function only knows that you're going to give it two variables named these things. So you can name it HT, you could name this Alfred. It doesn't really matter, except that 10 minutes from now, you won't remember why you thought Alfred was funny at the time. And it turns out that's not particularly helpful. So yeah, it can be HT. This could be caps lock area. There's a lot of different things that you could do in here, but this operation only happens inside of this function. So the function is not using the exterior variables. It's not using the public variables. It's only using the private variables that are defined here within the function. So it's only using B, height, and area, because those are the three that are defined within the function. Functions can make use of other global variables, and there are circumstances where you need to do that. But this height here and this down here and this, so this B and this B, even though it'll identify those as the same spelling, this B in the triangle area has nothing to do with this B in the Pythagorean, which has nothing to do with the B in the triangle height calc. They're all three separate versions of the same exact thing. So actually naming them differently is probably part of good practice. So the values, the way that these operate, slightly so I can see the questions a little more clearly. The values, the values are not supposed to be the same because it's just used within the function. Yeah, I want to be clear about that. It's really important for the sake of the library work that we're going to be doing. It's very important to understand some of these setup steps and how they operate. So we'll be happy to make that as clear as we can. Okay, so we now have enough to have the triangle area set up. We also need to figure out our third case scaling. So we have a switch statement. You can think of this like an operator switching board, which you've probably only seen reference to in old movies. But it allows for this process by which you can select a couple of different avenues for your program to follow. What that means is you will have more going on the you can have a lot of different things going on at the same time, and based on one of the things that we talked about last week was based on this variable, it'll select an integer that corresponds with the first case, the second case, the third case. So you can name them something other than case 1, 2, or 3, but naming them case and then the integer number that it's associated with simplifies the error handling later when we get to more sophisticated programs that throw error messages when something goes wrong. I understand that when you guys are trying to install software or you're trying to play a game and something crashes and there's error messages, I understand that it's frustrating and you're like, why doesn't it just work? The more you learn about code, the more you are amazed that any of this crap works at all. This is just a very tightly controlled language set, and it has to operate a certain specific way, and sometimes strange things can happen. So this is so I think case 1 and case 2 are done. So the equilateral case where two of the sides are the same side, the other side is the same size. We calculate the area. So this one should be fully covered now with what we have. The isosceles, this one, has two sides of different length. Then we switch, we use the side that isn't included in the comparator, and we break if that's the case. Else if side A and C are the same, then do these things. We break if that was the correct calculation. The else is the last remaining possibility where B is comparable to C. That gives us the calculation based on A, again, the one that's not in the comparison, gets the area based on that. Yeah, okay. So we step out of the switch case whenever, so we step completely out of the case and therefore the entire switch statement with these breaks. That's what these do. And this reports back those functions that we just set up, report back values that are then stored using that return. We're then storing triangle height calc to HT. We're storing Pythagorean to C, and we're storing tri-area to area. All right, so we have to finish up the scaling case and then break it. The default case we already set up. There has to be some kind of message that communicates the user did something unexpected, and therefore we have to try again. You don't have to be the same degree of snarky in your inclusions here, but it's sometimes more entertaining that way. All right, so in the example that we were working on, you were given a couple formulas. Let's see, we've got the Pythagorean. We need to incorporate the law of cosines, and we need to incorporate, so we're going to need we're going to need a law of cosines formula. That's going to need to be a function. We're going to need a Heron's law formula in the form of a function. Okay. Heron's law formula in the form of a function. And let's see, there's like a dogfight going on outside. Excellent. Most excellent. That's always exciting. We've got one other case that we need to calculate. This is where normally we would take, trying to remember now if there is truly an inverse in the math library or not. Let's see. This is another one where I'll have to consult the language reference. There's a couple different methods and mechanisms to do this. I don't have it up anymore. I'm trying to not have to also have you guys write a trig function for the inverse, because I think there are a sine let's see. I think, let's see if it recognizes. So there's a few steps. We need to determine an angle. That's a key piece of the puzzle here. We need to determine an angle between two sides. I think for this one, we can use the arc cosine and arc sine. I'm pretty sure. I'm pretty sure. So the area, we can't use the triangle area formula quite the same way for a scaling triangle. We have to break it up a little bit, and there's some kind of additional trig that needs to be done there. So there's some examples of what needs to be done. But I think we can use the arc sine. I think also the default arc sine, yeah, I think a sine. No, because a bunch of extras come up. So I think what we can do is use the arc sine. Yes, question?
Yeah, I could be wrong. I probably need to brush up on my trig, but don't you need more than two lengths of two sides in order to find the area of a scalene triangle? Like you would have to input an angle as well, I think, right?
Correct. That's why we're doing an angle determination. So this is part of the reason why I said if I try to help you guys walk through this whole process, significant and severe brain damage will likely occur last week. So that's why I was like, yeah, we're going to stop here. Because there's a lot that actually has to go into this scaling in order to make it work. So we have to use the law of cosines and Heron's law, but in order to determine what we do and don't have, this is also part of what we have to include. So the the best way to do that is, let's see, I think in the examples I've done in the past, I've had the user specify an angle between the sides. But this is another circumstance where I bet I can actually pull up let's see. It's helpful to know how to do it by hand. However, there is, I know there are some good examples and some bad examples. But I thought I remembered seeing somebody had a pretty nice flow chart because let's see. A lot of people have a flow chart for determination of which type it is. Um, but let's see. Yeah, so this actually is the Heron's Law and ARC formula are taking those into account. So I'm actually not going to incorporate the area because that's the basis for the rule. So this is part of the fundamentals of trig that you're going to have to be able to access and use later on in life because of just the way things function. But that is actually the correct procedure. So we're actually not going to be determining the angles between the two sides. We are going to be we're going to rely on Heron's Law first. So I think I'm going to move this one up and we'll see what information that we get from this. So Heron's Law calculation, this follows a couple key aspects that you need. So let's work on what does the Heron's Law need to do. What this is actually calculating is the with an angle we can use law of cosines, but there is a mathematical path to avoid that, and that's essentially the flow chart of what we are looking at now. You can use a semi-perimeter formula, and that's what's different here. So we're gonna change the direction of this a little bit using the Heron's Law and the semi-perimeter. So it's a special case, and it's entirely possible that none of you have actually seen this process. So the semi-perimeter calculation, we're going to do this. We are actually going to do this higher up so that we can do this first. So the semi-perimeter, just so that you guys know that I'm not just making up words. The semi-perimeter is a combination of things from the half-angle formulas, which I know all of you remember in great and gory detail. So let me share this. Yeah, the semi-perimeter. These should look familiar. The semi-perimeter is the sum of the sides divided by 2. When you then plug those in, you reduce down the law of cosines and the angles of all of the things drop out, and you use effectively this parameter and the 3 side lengths to do the calculation of the area. So there is a mathematical way to do it without asking the user for the angle. If they just took a tape measure, they measured 3 points, and they input the data, we can get the information back out. So that's something that we want to keep in mind. Let's go back to how we implement that. So the semi-perimeter calculation is done by, we're going to say SP for semi-perimeter. When we're defining this as a variable, again, we need to tell it, hey, we're doing something here. So we're going to do this as a float because that's the only thing that's going to make sense. Float SP is the SP is the sum of side A plus side B plus side C all divided by 2. What that does is that gives us the starting point to be able to then bring in Heron's formula for the area in the semi-perimeter form. And that gives us the information because the law of cosines is useful to get us the third side information. If we just ask the user for the 3 sides instead of asking them for the angle, which is much more complicated on the user input, this is all the work we have to put in on the back end to make the user interface simple and easy. This is the way that this works. So by now, you guys are probably all figuring out that by comparison, programming something like a voting machine, for instance, where this button goes to this candidate in memory, frankly, is just not actually that complicated. So we'll do probably something related to that later, but we're not going to do it today. So we calculate SP. We take side A, B, and C, take that semi-perimeter. Into that, we bring Heron's formula. So the area is, and this is, I'm going to use lowercase area because we So up here, we're going to need it as one of the things. No, okay, it's defined in the setup lowercase area. Okay, area. Got to use lowercase area because reasons. So area is equivalent to. We're going to need that square root function again. So square root. Now, this formula looks like the square root of the semi-perimeter. I'm going to narrow this down just so I can see it a little bit more clearly from what I'm doing here. Actually, we're going to turn herons into a function. Yeah. Let's do that instead. So I'm going to take these. I'm going to cut them. I'm going to drop it into a function because we want to do that. And rather than defining the function here, I'm going to say area equal heron. And we're going to define herons up here. There's some reasoning why. Let's see. Questions?
Yeah, I was just going to ask why it's better to define it at the beginning rather than in the case.
You can do it within the case. In this case, we're thinking in terms of how to have cleaner, more compact case switching rather than some of the other options. Basically, what we're trying to do is we're trying to avoid down here in the case structure from having to have things that are bigger and gnarlier than what they are here for case 2. So instead of redefining, and this particular function is not super duper huge, we just need to know what the inputs and outputs are going to be for this. It's not going to be hugely less work to do it this way, but this is a pretty reasonable way to do this. So we'll see what the area, we need to define this within area or within the function. So it's not really a matter of like, this is the only way to do this. This is the correct way to do this or anything like that. It's about trying to get to the maximum efficiency. So instead of this, we're going to have to define floats A, B, and C. So floats A, B, and C. We're actually going to be putting the side values into these, but this will be far more, this will be a little more compact format. This is something that later on, if you're trying to run a program and make it be modular, so that you can take these libraries functions, etc. You can use them later. What we'll do as an example after we do the lesson on these is we'll take these custom functions that we have come up with and we'll put them into Triangle's library and show what it looks like to use those Triangle libraries. The trick is there's going to be yet again some more steps, but I'm trying to teach you how to successfully get this program to run once first, then we'll go to the next steps. So this one, for Heron, this is what we're going to be inputting is side A, side B, side C. So this is calculating the area based on what has been input and stored to A, B, and C. So it's a little different than if we're working based on two sides and an angle or something like that. So we'll look at more people having fire drills and connection issues, of course. All right. There we go. So we're taking this part of it and we're saying a square root of, and this is going to be SP times our first one is SP minus A times, this is directly from the Heron's formula itself, SP minus B. So we need each of those differences to be calculated. Then we need the products of those differences. So we do have to pay very careful attention to order of operations and all that stuff that when you were learning it, you went, when am I ever going to use this? It turns out in order to solve real problems, you have to really know lots and lots and lots and lots of things. So square root of SP times SP minus A times SP minus B times SP minus C. We have the correct number of open and closing parens, and we have our semicolons to close. So this allows us to take in these variables. If we were to have done it a little differently, we would have to write side underscore, side underscore, side underscore for all of these different things and then brought in the SP. So the function here doesn't necessarily save you tons of space, but if you had to type this out more than a couple times, having it be, so if we had to use the same Heron's formula for two of the different triangles, that would save us a tremendous amount of work and effort. So having it in a function helps because you can call on something repeatedly when you don't want to have to type out all the gibberish each and every single time. And the last thing that we need to do is return the area, but we have to do, we don't tell it that this is being defined, it's going to give us a conniption fit. So that's what this is known best for. All right, so we have our Heron's formula. We get the area back out as a floating point value. So area equals Heron, side A, side B, side C. So then instead of, especially if we were not doing the three sides, if we weren't taking the three sides in and we only took in two sides from the user, here we would have to have another whole series of lines about the getting an input for the angle, and then we would have to determine whether the user put the angle in by degrees or radians. And so then we'd have to have if statements and all kinds of other comparisons. So the example of this looks completely different. And so here, by having the three sides, we're about 135 lines. As kind of another reference point, this kind of determination is, under other circumstances, this kind of program can easily span many hundreds of lines. So it's very easy for this, instead of being like 130-ish line program, it's very easy for this to be like a 220 line program if we have to do all of that extra comparison and bring in angles and all the other things. So I think I did an example like this where I want to say we ended up somewhere around like 250 lines ballpark, 230, 250, something like that. So it was a lot. It was an awful lot. Might have been like 230. So an extra 100 lines of code if we don't make use of functions and make things a little more compact by using smaller variables and all of those sorts of things. That also reduces the overall memory that the program takes by a small amount. So the board that we need to verify this for, I need to connect it first. Otherwise, we won't be able to select it, and I can't do a verification. Okay, where did it find the first error? Before break. Where? Here we go. 94. Aha. Yeah, I would have expected a semicolon there as well, area. And since I copied, the area came up as an issue. Make better life choices, like including a semicolon at the end of everything when in doubt, semicolon all the things. All right. See, snarky comments often come back to bite you. It's just the way things go. All right. Let's try that again. Aha, perfection. Excellent. Okay, so we need a couple more pieces to the puzzle. Okay. All right. So I'm going to go ahead and drop this onto the board. And I'm going to bring up the serial monitor. Not connected. So we're actually not going to be using pi in that calculation. You guys have probably figured out. I originally thought we were going to go down the angle path. That was going to be the need for some of these extra variables. So the length of 3 sides, it's going to calculate the area and output the triangle type back to the user. So that's still true. Not everything that you've seen in your life is a lie, just most of it. So let me do a reset. Okay. So we're going to say equilateral. Length of one side, we're going to say 2. Three. Hello. 4. Why can't you parse the integers? Yeah, so maybe don't use Arduinos as the main computer on the Mars lander is what we've determined here. Well, there we go. Length of the second side. So it's why that delay? That is
Is it waiting for the timeout?
it is probably waiting for the timeout. Let's see. That is probably actually what it's doing. It's supposed to run the timeout. I wonder if that's an order of operations thing. So I'm going to test it with 1 and 2 and see, because the timeout is the limit and it shouldn't matter whether I'm telling it in order here or not, but that might actually make a difference. Because it might be moving forward with a default answer regardless of what it's doing. So let's have it run the timeout after. I don't know that that should make a huge difference, but we're going to save and load just in case. Come on. Save. We're going to reload this. I'm going to reload the serial monitor. So I'm going to say equilateral. Please enter the length of a side. Okay. So it is responding more quickly. That time it didn't. So it responded more quickly for the first one only. So it's waiting for the timeout on this one. Why? Why? The third side. So the third side, yeah, see the timeout is after. Because it shouldn't be timing out anywhere else in this process. So it shouldn't do the full 15 seconds if it successfully parses the integer. This now gets down to the weirdness between the board and the cable and your USB port and whatever USB to serial conversion has to happen there. Yeah, it is definitely waiting for the output. Okay, so it actually reached completion, but I want to see if you guys know why. So it's not that it's not taking in the input, it's done the calculation. I want to see
Did
if
we
you guys...
not do a print of the answer?
Correct. So turns out when you don't print the answer, it doesn't print the answer. See, sometimes I leave some of these things in just as stumbling blocks so that you guys run over them, trip, fall on your face, get a mouthful of sand, and then learn new things, like never trust the instructor. The key here is really just to output based on the area. So then, because of the way that we've set this up, I wanted these to break out. And regardless of what happens as it breaks out of the switch case, which is here, this is still within the setup. Now we do so serial print. And then serial print line. I wondered why it felt like it was done, except it wasn't. That was an indicator. Don't forget to print the output that you worked so hard to get. See, it's not the complex things that cause me personally to trip. It's the stupid little stuff like, hey, how about print out the answer? Area. And then you could take a gander at units, but just because actually we're going to print the area. We're going to print line, space, unit squared. That way Professor Tomford doesn't have to get after you with her unit corn, and you will remember always to do units. Never anger the unit corn. All right, so I think the rest of that will be okay. All right. We can do some more logic on this, but there's a good reason to want this to work the way that it does. I'm going to reload. I'm going to save. And I'm going to look at the serial monitor. 1, 4, for, so this second one should be instantaneous as soon as it detects input. But it does not, because even though we have the timeout after parse integers, it's still behaving the same way.
Professor Kyle,
Yep.
my program seems to work, but I don't know what the difference between ours is.
Well, this should work. There we go. So it's outputting the area correctly. But why it is still pausing for the full 15-second timeout when it should be parsing the integer first is curious, because it's behaving like it's hung up on the serial not being available. So unfortunately, because I've included this, if for some reason between my specific example of the board, the specific USB cable I'm using, the USB interface that it's plugged into, the relay cables from the front case USB to the motherboard, all the way down to the specific versions of drivers of the USB, there could be a timing delay somewhere in any one of those steps that makes it seem as though there's nothing for it to do the parse on, or it ran the parse too quickly. So it might actually be effective instead, because of that, to add in a like 100 millisecond delay or something after this while not serial, before it tries to do a read, because it might be skipping over multiple times. That's a possibility. Yeah, question?
Yeah, so mine's printing, or it's asking for the side 1 and side 2 at the same time. It's not waiting for me to input something for side 1. Is that the same issue, I guess, the USB cable or whatever? Yeah, okay.
Yes. So this is where it gets into, this code is correct. Now, how your actual physical example of the hardware behaves is different because your favorite answer reasons. There isn't a one size fits all. Like I said, that delay instance, I'm going to do a test real quick to see if this works. But you also have a lot of different variations of these boards. I think they're all made by a handful of manufacturers. I don't think there's as many folks making the Playground Express boards as there are the Arduino Unos. There's got to be a couple dozen different manufacturers at least of the Arduino Uno boards, because the whole idea was for everything to be outsourced and open sourced and all the sources. So it's been outsourced and it's been open sourced and it's been all over the place, and they build them sometimes from the cheapest possible components they can. So each, if you were to compare, if you were to even have something like a countdown timer running on 100 of these boards all side by side, one of the things that you would likely see is you would see differences in how quickly they counted down. One would go just a little bit faster than the other one. One would hang up a little bit and do weird things, you would see a lot of different results, and you would have some ending seconds ahead of others in a countdown for the same number of clock cycles, because the variation in part quality and solder joint quality and whether or not that board was made during COVID on a Friday, or like, now you get into variations of the hardware itself. So if we do a reset, this should come back up, ask again. I'm going to say isosceles, and I'm going to say 4. I'm going to say 4. Yeah, so I'm going to add in the delays to this, because there shouldn't be a delay on second entry. 4. There shouldn't be a delay on second entry. That is so curious. Then once it finally times out, I do a 6 for the final side, and it'll output the area. Yeah, see, in that case, it's going to both the timeout. There's also a way that you can take the parse integer outside of the while serial available. So you could have it do a timeout, maybe even a break or something like that. Okay, so this one, it took all of the integers into account. This one, I only entered one integer, and it took that into account. So that's why these delays can do weird things, because this first answer just crashed the probe into the surface of Mars, and somebody got fired. The second answer is actually correct. So this is where there has to be kind of some troubleshooting, and sometimes the order in which you execute these is going to matter. Simply by implementing, like, A actually seems to work just fine. So I'm going to leave A alone. I'm going to implement it on B. I'm going to do just 100 millisecond delay just to cool its jets for a second in between those parameters. Because then you really don't need the timeout to be any longer than about 2 seconds on these guys. Because if the user is engaged, I think this will fix the timing. We'll see. Let's find out. So we might have to do a reset. There we go. So we're going to do isosceles. 4, 3. See, it's still delaying on the second side, and it's delaying longer. And 4, so it is actually an isosceles, 5.89. Okay, so it is calculating correctly based on what I'm inputting. But that timing, so the timing on the third one is much better. I'm going to try this one more time to see if the timing is fixed. So let's do isosceles. The length of one side, 4. The length of another side, 3. Nope, it is still counting down the whole 2 seconds. So it's still running the time delay, but it's not running the time delay from A. Very curious. Okay. So we can get the same answer. We can get it repeatedly. It's doing the thing it's told to do, more or less. But yeah, you're going to be into particulars of your physical individual hardware. Again, some of those variations are why I was going to try and use the Arduino kits that you already had, but it is what it is there. All right, so one more time, just to validate, it's going to be a scalene. 3, 4, and it's going to take the full 2-second delay. That's frustrating, but it is what it is. All right. 5. So what might need to happen there is the set timeout. That's supposed to only be there as a fail-safe. It's supposed to exit once it's parsed the integer and it detects that there is serial data there. But it's super duper interesting. So 3, 4, 5 triangle. Triangle area is 6. Okay, so it does do calculation based on that. That actually sounds right from what I remember. Or it's very close to. The variations of the isosceles triangle, when it's a right triangle, there might be some issues with this in terms of rounding, but this at least will give you a pretty good idea. But rounding errors and reducing those is why I have you guys using floats in this particular program. So, all right, I think that's enough to at least demonstrate the concept. Awful lot of work to get the area of a triangle. However, we can now use that. So I'm going to switch gears a little bit here. I'm going to stop the recording there. And we're going to go to a little bit more in depth on functions, but we're going to do it using Dr. K's content, which I've found to be the most time efficient and in depth.